Likely you are aware of this, but exam 3 is on us in just a couple of days. Wednesday this week instead of Thursday. I don't know why the registrar was not able to provide us with our Thursday request, but I have to live with what they give us. If you have a legitimate conflict, then I need a note from you so as to indicate the nature of the conflict, your name, email contact information, and an indication of your ability to take the exam earlier on Wednesday, noon to 2 p.m., 2 to 4 p.m., or 4 to 6 p.m. Wait a minute. We got class then. Forgot that part. Now, anything we'll do on Wednesday will be done strictly to support your ability to wrestle successfully with the exam. That I can promise you. And I've told you the need on your part to take a look at video 037. And as I've noted up here, video from July 24, which you need to start at about 20 minutes in. Maybe it's 21 or 22 minutes in. I think it's about 22 minutes in. As the first 22 minutes is silent. I forgot to turn on the microphone. It really doesn't matter because what's covered in the first 22 minutes of this video is covered in video 037. So no loss. It was a review. If you have questions regarding this stuff from the videos, your questions will be entertained tomorrow during discussion class. What are these videos about? Well, if you did what I asked you to do, you know. In Chemistry 2045, you examined periodic size trends because atomic size is very important relative to what we want to get at, our main goal regarding Chapter 23. And that is to establish a foundation for being able to rationalize strengths of Bronsted-Lowry acids and bases. So far, as we did, for example, in Chapter 18, was to show you a list of these acids and bases in order of relative strengths. But we made at no time any attempt to explain why these acids show the strengths that they do. That's what we want to do in this chapter. And the first and foremost consideration upon which this rests is atomic size. We'll provide an example in a few minutes. So, in order for you to understand the trends that you observe in atomic sizes as you examine the periodic table, that's what's in the videos. That's what you talked about in 2045, presumably, but if not, it's in the videos. At the minimum, I trust you remember, that atoms compare how size-wise within an A family. Lithium through neon, sodium through argon. How do the atoms compare size-wise? As we go left to right across a period, the atoms get smaller. Do they get substantially smaller as you go from atom to atom? No. Usually not. A steady shrink in size is observed, but usually not much shrink as you go from atom to atom. However, when you go from lithium to neon and sodium through argon, since you've now gone across 8 atoms, in transcending the period. When you go from lithium to neon, you wind up with a big size difference between neon and lithium. Lithium being a lot larger. Sodium being a lot larger than argon. How about in family size transfer of A family atoms? Lithium down the family to cesium. Never mind francium because of its radioactive character. Beryllium on down through barium. The atoms are getting larger. As we go from period to period, lithium, sodium, beryllium, magnesium. Do we see a small shrink in size, or generally a much larger, a small increase in size, or a large increase in size? Large. All right, that's good. The explanation of this is what's provided in the videos. And 2045 folks tell me they do this in 2045.
Will we be held responsible for those 2 videos on the exam on Wednesday?
Sure. Of course. To the extent that understanding what's in the videos will allow you to understand what we're going to talk about. That's the important part. Now, before we carry on with that, let's go back and finish chapter 22 on electrochemistry. The only remaining issue is that of derivation of E0 for a new half cell. There are examples provided regarding this in the notes. Examples which rest on the illustration that you can oftentimes synthesize new half cells by just arithmetic combination of 2 other half cells. Get a new half cell. Not a new cell reaction, a new half cell. We've showed an example right here. This is part and parcel of question 22, question 32 from chapter 22. If I add these 2 as written, I get this. What's E0 for this? Here's the problem. Because I do not get E0 for this new half cell by adding these E0s for the half cells from which this was synthesized. Net cell reaction, yes. Works for net cell reaction, why? Because when we combine net half cell reactions to get a net cell reaction, we have no electrons left over. But when you put together half cells to get a new half cell, you wind up with electrons. What can we add? Can't add the potentials. What we can add are the energies. So what underlies this issue is application of this relationship to each half cell, and then ultimately to the half cell for which we wish to get the E0 value. Because from this, you take into account the number of electrons transferred with the n value. You get delta G0 for the first half cell, delta G0 for the second half cell, add those up, and that gives you delta G0 for the third half cell. And then apply to the third half cell this relationship with n being 3 for the third half cell in this case, and calculate E0. Well, that's not difficult. Requires some arithmetic. But there is an easier way. At least I consider it to be easier. The easier way is to, in essence, do what we did at the end of chapter 21 to calculate Ka values for the very strong acids which we see appearing in our acid-base table. By using information from table 1 at the end of chapter 20. We use that information, for example, to recognize why carbon graphite is the thermodynamically stable version of carbon rather than carbon diamond. So get out Table 1. You needn't do that now because I've got the pertinent data on the board. And for the half-cell reaction, the new one, for which you don't have the E0 value, use table 1 to get the standard free energies of formation for each component of the half-cell. Then apply Hess's law. This allows you to get straight away delta G0 for the half-cell reaction, which is what we did with this procedure that we just talked about and which is illustrated in the notes. But rather than calculating delta G0 for each of these half-cell reactions, we don't even have to bother with these half-cell reactions, which in this case were put together to get this. Just deal with the half-cell reaction for which you want the E0 value directly. Get out table 1, look at the standard free energy of formation information, apply Hess's law, get delta G0 for the half-cell, and then use this to get E0. That's all there is to it. Keeping in mind that you now have to recognize a thermodynamic formality, and that is, if in the thermodynamic properties data table, table 1, you see this formula appearing rather than this formula, and for this formula you see this delta G sub F super 0 value tabulated, minus 4.7. That is not the delta G sub F super 0 value for this thing. I really don't know, I haven't found out yet why thermodynamic folks do this. Because in reality, there's no such thing as this. Because the positive charge density of iron plus 3 is substantial. It forms a defined hydrate in water, and this is the defined hydrate. But what we need to realize then is if you see this formula in the table, rather than, as is this case, this formula. This being the formula for the stuff that's involved in the half-cell for which we want to get the E0 value. How do you get delta G0 for this thing? You add delta G sub F super 0 for 6 moles of water liquid to this, and then you get this. That's why I wrote this. Here's delta G sub F super 0 for water liquid times 6. The formula contains 6, so you're going to add 6 times minus 237.1 to this number to get delta G sub F super 0 for this. But now we realize we don't even really have to bother with this, do we? Because you'll have 6 times this from this side of the equation, and 6 times this from this side of the equation. So for this half-cell reaction, there's delta G0. Put it in here. N is 3. Use the Faraday, and you get E0. All done. I think simpler than the formal process which electrochemists use to get these E0 values calculated for new half-cells. After I came upon this recognition, I said, when I rewrite the notes, I probably won't even use this other method. But that's what you'll see in texts on electrochemistry. So at the minimum, I thought I'd put it in there because if you go on and do some more chemistry, you're going to see that, I'm sure, advertised in a class on electrochemistry or in a physical chemistry class where electrochemistry is considered. Another example, this is shown you on page 2229. So for this case, for this 0, this is the standard state copper. 2 moles water liquid, 2 moles hydronium ion aqueous. So we can forget that from the arithmetic. Do you remember why? Do you remember that delta G sub F super 0 for water, liquid, and the hydronium ion AQ are the same? Because delta G sub F super 0 for H plus AQ is nothing by definition. So when you add H plus to this to make it hydronium ion, you haven't changed its free energy. So, you get out the table, look up delta G sub F super 0 for this, delta G sub F super 0 for this, apply Hess's law. And then this relationship where for this transformation n is 2, done. So on with chapter 23. A few moments ago, we reminded you that size considerations, atom size considerations, are very much a part of this. We'll show you an example in a moment. Tell me, what other property for an atom or a species derived from that atom, like an ion, you think will relate very much to negative charge density stabilization? Why are we considering negative charge density stabilization? If we're looking at the difference in strengths between two Bronsted bases and know that one is stronger than the other, which of course must be the case, do we not then immediately know how the strengths of their conjugate acids compare? Yep. The stronger base has the weaker conjugate acid and vice versa. So the way we're going to play this game is by necessary and appropriate considerations like atomic size, etc., is assess negative charge densities for bases, specifically the conjugate bases of the acids whose strengths we wish to be able to rationalize. Because when we know the relative strengths of the bases, at the same time we will know the relative strengths of their conjugate acids. All right? So I ask this again. Besides atomic size, what atomic property did you learn about in Chemistry 2045 that we've talked about previously this term, but not in detail? We will now. Which is reviewed by these videos I've asked you to look at. Relate very much to stabilizing negative charge density. What atomic property am I referring to?
Electronegativity.
Electronegativity, you betcha. Do you remember trends in electronegativity? I should think you do. We've talked about that previously. I've foisted upon you my device that I give my students in 2045. It's a lot of fun to think about electronegativity. Fun, fluorine, oxygen, nitrogen. Chlorine, essentially the same electronegativity as nitrogen, but there's a heck of a lot more important compounds with nitrogen in their composition than those with chlorine in their composition. I think it's fair to argue that amino acids are a lot more important than sodium chloride. Maybe you see it oppositely. Maybe you think that trying to eat popcorn without sodium chloride is terrible. But without amino acids, you wouldn't have the popcorn. So there. So, in brief review, how do electronegativities compare for atoms which are related to each other by being in the same period? Lithium through neon. Electronegativities increase as you go left to right. And indeed, in period number 2, you wind up getting to fluorine, which is the most electronegative atom. Why is there not an electronegativity value tabulated for neon? Why is that? The answer to this question lies in knowing the definition of electronegativity. What is the definition of electronegativity?
The ability to stabilize negative charge, the relative ability.
You got to say a little more.
The relative ability of a nucleus.
It's a measure of the ability of a covalently bound atom. Therein lies the rub of the grin. A bound atom to stabilize negative charge density. Neon has not yet been found to make any bonds. So how can we assign to it any electronegativity? All right. And inside a family, electronegativities do what as you go top to bottom? They decrease. How about the halogens? 4.0 on the Pauling scale for fluorine. You know part B, the Pauling electronegativity for chlorine? 3.0, some tables show 3.1. How about bromine? I'm just curious if you know this. 2.8. Iodine. 2.6. So we're seeing as the atoms get larger, the difference in their electronegativities decreases. Now, with that having been said, we'll list atomic size, we'll list electronegativity as factors upon which negative charge density stabilization depends. We'll show examples in a moment. But now I'm going to operate on electronegativity and extend it to include a consideration which also relates to this issue. Have you read about this in the notes? Anybody know what this stands for? That part's electronegativity. This is orbital electronegativity. All right? So I've written down designations for atomic orbitals and hybrid orbitals. SPDF are the only types of atomic orbitals which as yet we've had to pay attention to. Because even for the most electron-rich atom, which is now known, that's number 118, G electrons are not yet required to develop and account for and describe their electron configurations. We got to get to 121 electrons total before we need G electrons. I'm not going to worry about that. Because at the minimum, we already know enough about these atoms to realize that even if they are synthesized in nuclear reactors, they have half-lives which are far shorter than that. So I don't think we're going to go in a laboratory and do much practical chemistry with these atoms. If you're an electron and you move into an orbital because you're moving into an energy level, and as we know, at least from the rules of quantum mechanics which we apply to this, atomic electrons live in orbitals. You're moving into an energy level, and in this energy level you see before you a vacancy sign flashing in front of S orbital, P sublevel, D sublevel, F sublevel. S sublevel, single orbital sublevel. Like an energy level number 4. 4S, 4P, 4D, 4F. They're all there, they're all vacant. You, Mr. or Ms. Electron, in which of these orbitals do you take residence?
S.
S. Why? because it's the most stable, lowest energy orbital in which you can reside. And that's the way material behaves. That's the way electrons behave. In the environment in which they are placed, they will always assume the position from a thermodynamic standpoint of lowest energy, because then they're most stable. That means, from an orbital electronegativity standpoint, for atomic orbitals within an energy level, S has a greater orbital electronegativity than P, and P has a greater orbital electronegativity than D, which in turn has a greater orbital electronegativity than F. In fact, we'll take F out of this consideration because, practically speaking, F orbitals and F electrons are not part of the valence environment of atoms, which means they're not part of chemistry. There are some exceptions to that. We don't care about the exceptions. All right, now let's apply this to hybrid orbitals. SP, SP2, SP3, SP3D, when d orbitals become involved. And I think we've already brought to your attention the fact that when you've got 5 orbitals, since you have 5 orbitals in the d sublevel, you can make hybrids all the way up to SP3D5, which is a grind, a blend, a hybrid of 9 orbitals. S, 3 Ps, 5 Ds. All right? So here you are, Mr. or Ms. Electra. You have the opportunity to take residence in a hybrid orbital. They're all derived from orbitals of the same energy level, like energy level number 3, because energy level number 3 is the first energy level that we find d orbitals to be part of. They're all there, and they're all vacant. At least we so imagine. In which of these hybrids do you take residence?
SP.
SP? Correct. Why? Why is SP most stable of these hybrid orbital types? If we've recognized that for atomic orbitals, S is of greatest orbital electronegativity, it's most stable, lowest energy, then any hybrid synthesized from an S orbital will have a contribution made to its orbital electronegativity by its S orbital composition. This hybrid orbital is 50% S character, isn't it? This hybrid orbital is 33 to 30% S character, isn't it? This hybrid orbital is 25% S character, isn't it? This hybrid orbital is 20% S character, isn't it? That means this hybrid has the greatest orbital electronegativity of any type of hybrid orbital because it's highest in S character. Just to take off from this, applying it to hybrid orbitals. Now let's put it to use. This orbital electronegativity business. Three nitrogen-hydrogen molecules. Now, none of these molecules are strong acids by any stretch of the imagination. They are at best very, very weak acids. But still, with orbital electronegativity, we can line them up in order of acid strength. What do you think we should do first with these molecules? How about that? Come on, get at it. You got 5 seconds. Did you get these? Now let's strip H+, because we have said that The way we're going to play this game is to assess effective negative charge density on conjugate bases. Because any base, by definition, has got to have a degree of negative charge density. There's our three conjugate bases. Which of these bases is most stable? Because that base which is most stable has the conjugate acid being the strongest of these three. Which of these bases is most stable? Notice that size won't mean much in this analysis, because the negative charge in question is residing on a nitrogen atom in each case. Well, let's get at this orbital electronegativity business. Tell me, how's this N atom hybridized? If you don't remember, I'll put the H back. H plus. How's this hybridized? Tell me and I'll write it down. If you cannot determine hybridization, which is something that comes from 2045, you can't play this game. Did you learn how to determine a hybridization for an atom in 2045? Which we also emphasize in 2045 laboratory, assignment 6 on models. The easy way to do it is with the Lewis picture. That's why we started with the Lewis picture. Count the number of sigma electron pairs. Sigma electron pairs for the valence environment of the atom in question. How do you count sigma electron pairs? You remember that at each bond site, how many sigma electron pairs are present? 1. And what's the other part of this puzzle? Non-bonding pairs. How do non-bonding pairs count? Are they sigma? Are they sigma? Yes. And that's the way you play the game. One, two, and one of these pairs is sigma, right? At each bond site there's a sigma electron pair and only one. 3 sigma electron pairs. Which of these hybrid orbital types will accommodate 3 sigma electron pairs? Did you learn that hybridization applies strictly to sigma electrons? 2045? Strictly to sigma electrons, not pi electrons. Which of these hybrid schemes accommodates 3 sigma electron pairs? Which one of these is a blend of 3 orbitals? sp2. You can count, you can play the game. First you got to count the pairs, then you got to count which orbital, hybrid orbital type accommodates that number of sigma pairs. sp2. How about this? How about this? Greatest orbital electronegativity? sp2 nitrogen, right? That means the electron density on this nitrogen atom is stabilized to a greater extent or lesser extent than the negative charge density on these nitrogens. Greater extent, which makes this the most stable and weakest of these 3 bases, which makes this the strongest acid. And that's how the game is played. Now how about these 2? Now we're going to have to look a little bit further. And we're going to apply another idea, which is based on electronegativity. It's called induction. These are each sp3 nitrogens, aren't they? So in this case, we can't decide which of these bases is weaker and more stable based strictly on orbital electronegativity, because the orbital electronegativity consideration gives us sp3 for the same kind of atom, each with a single unit of minus charge. So what's the difference? Which of these bases is weaker and more stable? The answer is this one. Why? The answer lies in induction. Tell me, how does the electronegativity of nitrogen compare to that of hydrogen? N is more electronegative than H. Guess what? That means that this nitrogen, which is covalently connected to this nitrogen which bears the negative charge, has what impact on this negative charge density relative to the hydrogen atoms? Because nitrogen is more electronegative than hydrogen, isn't it? Right? That means this nitrogen exerts a greater inductive stabilizing effect on this negative charge density than do these H atoms, because nitrogen is more electronegative than hydrogen. You know what the word induction means, don't you? To induce something to happen. Nitrogen, because of its greater electronegativity, induces a drain on this negative charge density. Pulls it this way, if you will, relative to what's going on here, because H atoms are much lower in electronegativity than nitrogen. These don't stabilize this negative charge density at all. But this nitrogen atom does, because it's more electronegative than hydrogen, and a good deal so. So, we've taken a peek at electronegativity and orbital electronegativity, and a peek at induction, and the only other thing that we will talk about of consequence, which you will do tomorrow in discussion class, is how size relates to this. And what we're going to do is to assemble a collection of considerations that we need to think about every time we want to make a decision on effective negative charge density, on how stable a base may be, so that in turn we can decide how strong its conjugate acid is, or weak, whatever the case might be. Size, electronegativity, orbital electronegativity, induction, and I'll bet, even though we've not yet talked about this, you could name at least one other factor. R, E, S. Yeah, how about that? Pick it up from this point tomorrow.